hold on. Go. This unit is Oxidation Reduction unit. We call it redox for short. So from here on out, I'll refer to this as the redox unit, which is just oxidation reduction put together. Okay? It is a different kind of reaction. Well, it is, but it isn't. There's several actually kind of reactions that we've studied that actually end up being redox. But what makes it a redox reaction is when electrons are being transferred between the reactants. So electrons are transferred between the reactants. So we'll actually be exchanging the electrons. Okay? Now, okay, the oxidation reduction reactions, like we said, we call them redox, so how we'll refer to them, are another type of chemical reaction. This says in addition to those what we've already studied, but you'll see that the ones that I have in red, synthesis, decomposition, combustion, and single replacement, those actually are already redox reactions. We just didn't study them that way because we didn't talk about electron transfer. Okay? Double replacement are not. Okay, they're not a redox. Okay? So, oxidation numbers or states are something that we are going to have to assign. They're kind of like charges, but not. Okay? They're kind of like charges, but not. So an oxidation number, or sometimes it's called oxidation state, is a positive or negative number assigned to the atom according to a set of arbitrary rules. Okay? Once the oxidation number has been assigned, you're going to use that to determine whether that element underwent oxidation or reduction. Okay? They always go hand in hand. Okay? And unlike charges, oxidation numbers actually don't really have a physical meaning. It's just kind of a way for us to understand what's going on in terms of the electrons. If it is an ionic compound, the oxidation numbers are going to be the same as when we did ionic numbers. Okay? It's when we're talking about covalent, because what are covalent compounds doing with their electrons? Sharing. Okay? So they're going to be more than those where the rules get a little bit different. Okay? This is the set of rules that we're going to use for oxidation states. Okay? And they're used in order. So an element in its free element in its natural state is always going to be 0. Just like for charges, there's no charge on copper by itself or iron by itself. Okay? Chlorine gas by itself, still Cl2, but its oxidation state would be 0. Okay? If it's a oxidation state of a monoatomic ion, mono means one ion, it's the same as its charge. So sodium, +1. Its oxidation state would be +1. Okay? In compounds, fluorine is always going to be -1. Okay? Always. Oxygen is going to most of the time be -2 unless it's in a peroxide, such as hydrogen peroxide. Then oxygen's a -1. Okay? Hydrogen is +1 in covalent compounds, but if it's in a metal hydride, that's supposed to be negative. Sorry. Change that to -1. Sorry, I just caught that. Okay? And then when we're doing our oxidation states, just like when we were doing ionic compounds, the sum has to equal 0 if it's a neutral compound. If it's a polyatomic ion, it has to equal the charge of the ion. For instance, if we were doing sulfate, the sum of their oxidation states would need to be a -2 because that's the charge of a sulfate. Okay? So let's do a couple because that sounds kind of confusing right now, right? Okay. Huh? So lithium, what would the oxidation state of lithium be? 0. It's an element. So it would be 0. Okay? When we're looking at calcium carbonate here, okay, here's what I suggest. Because carbonate is a polyatomic, I'm going to pull it out separate. Okay? So calcium is a group 2 metal. It's going to have the same charge as what it normally does. So if its charge is +2, its oxidation state is +2 because it's a monoatomic ion. So calcium would be +2. Okay? Now we're going to go look at our rules that we're supposed to use in order, and the next one that would show up would be that oxygen is a -2. Okay? Unless it's a peroxide, which this clearly is not. So oxygen is a -2. Okay? So now I'm going to decide what carbon is. Okay, carbon shares its electrons. It does not have an outright charge. So we're going to figure out what its oxidation state is. Okay, so here's how I'm going to do this. Okay, I have 3 oxygen, yes, at -2. So what's its total? -6. So I basically need to see what does carbon need to be so that the overall charge of that polyatomic is a -2. So you can do it in your head, or you can say -6 plus x equals -2. What's x equal to? 4. So you can do it that way, or you can look in your head and go, it's got to be a +4. So the carbon's oxidation state would be a +4 in this compound. It can be different in different compounds. Okay? So on your next page is going to be a left side, but give me, oh, I'll look at it. I have it right here. I was going to do 1 or 2 off of there, just so you kind of know what's going on. I'm actually going to do 2 of them so you can see how they change. So we're going to do sodium nitrate and copper nitrite. Copper 1 nitrite. So we're going to do this charge of sodium, nitrogen, and oxygen in this one. Okay? So we know sodium's going to be what? +1, because it's monoatomic. So now we got to figure out the ones in that. Okay? So we said oxygen, unless it's in a peroxide, is going to be a -2, so we know that one. Now notice when I'm doing them down here, I'm telling you what the oxidation state is individually of the oxygen. To go up here, I've got to figure out, I've got a -6 total. So what plus a -6 is going to equal a -1? So what's the oxidation state at +5? Okay. Now if I do this one, okay, copper, which copper do I have here? +1, because I'm with nitrite. Okay, so oxygen's still a -2, but what's nitrogen going to be in this case? 2. This is a total of a -4. What plus a -4 will equal a -1? 3. So nitrogen in this case is +3. Okay? Is that making sense to you? I would suggest tonight you go home and do the left side, or here in a minute, while it's fresh in your mind, and then it becomes a little bit ingrained in your brain. Okay? All right. The reason it's important to be able to do this is because when you're looking at when we get to the reactions, you have to recognize if it's a +3 on one side of the equation, and then we do a reaction and it ends up being a +7 on the other side, you have to realize, okay, it went from +3 to +7, it lost 4 electrons. Okay? And then so it was since it lost electrons, it's oxidized. So that's what we're going for. Okay? All right, so let's go to the next set. I went too far. Hold on. So oxidation reduction reactions are going to be written as half reactions. Okay? And they always occur together. So write that big. Always. You cannot have reduction without oxidation, and vice versa. Can't have oxidation without reduction. Okay? They're always hand in hand. So let's decide what's oxidation. Okay? The oxidation is the loss, complete or partial, of electrons. So it's the loss of electrons. So when the element loses electrons, remember electrons are negative, its oxidation state will become more positive because it's losing things that are negative. Okay? So for instance, if I have sodium metal, if it loses its electron, it goes from being a 0 to a +1 on the other side. And then you'd have 1 electron out there because it lost an electron. Okay? If it is a complete or partial gain of electrons, the element gains electrons, and its oxidation state will become less positive. And the reason we say less positive instead of more negative is because you won't always have a negative oxidation state when you're gaining electrons. You might have had a +7 and you gain 5 electrons and then you go to a +2. So you're becoming less positive. So that's why we don't say more negative, because we might not, that confuses some people because we're not always negative. Okay? So here is an example. We have sodium plus chlorine gas going to NaCl. Okay? Remember, we're going to break it up into the half reactions. Thank you. Okay? Sodium, in this case, is gaining 2 electrons. It's actually only gaining 1 electron because of the 2 and the 2. But the charge is going from 0 to +1. So since it got more positive, it is the one that's oxidized. Okay, because it got more positive. It lost electrons. Okay? For the half reaction, for reduction, it's gaining electrons. The chlorine went from a 0, okay, gained 2 electrons, to go to a -1. So it gained electrons. So it's reduced. Okay? Is everybody okay with that so far? So then the overall reaction looks like that. This is your half reaction for sodium, which is oxidized. Good luck.
Thank you.
This is your half reaction for reduced, which gained electrons. Okay? And later on we get to learn to balance them.
Oh my God.
I love balancing redox reactions. They're my favorite, actually. Okay? Here are 2 ways that you can remember it. Okay? This is the one I use all the time, oil rig. You will probably write that on your test. Oil rig is oxidation is loss of electrons. Reduction is gain of electrons. That's a way to help you remember when you're doing it. Okay? Because it gets a little bit confusing. Or maybe not confusing, you just can't remember which is which. The other one, which other people use, I just don't use that one as much, is Leo the Lion says grr. And when I did this, yeah. Excuse me, this is supposed to say losing. I covered it up accidentally. Losing electrons is oxidation. Gaining electrons is reduction. Okay. I learned it as oil rig, so that's what I'll use. But you can use the lion one if you like lions. Okay. So that's to help you remember which is which. Okay. And I'll usually say, if you get confused, I'll say remember oil rig. Okay. Oxidation is loss of electrons. Reduction is gain. Okay. A couple more definitions, and that is going to be it.
That's the worst font ever.
That's already on your notes. That's just telling
This
you.
looks like bad vision.
Yeah, I got all my glasses on.
Oh,
It hurts.
yeah, it's not.
Okay, I will change it later. But if you are looking at a reaction and you don't change your oxidation numbers on the sides of the equation, then you don't have an oxidation reaction, a redox reaction. So you always want to check your. You always want to check. I'm sorry, I will change the slide. Okay. You always want to check your oxidation states on both sides. If there's no change, then you don't have a redox. You have something else. Okay? Okay. Last set of definitions, and then we are done for today. Okay? The reducing agent, this is where you have to really stop and think about it. The reducing agent is the substance that loses electrons. Okay? But that substance is oxidized. Because if it's oxidized, it's called the reducing agent because it causes the other thing to be reduced. Okay? The oxidizing agent, okay, is gaining electrons, but itself is reduced. And it's called the oxidizing agents because it's reduced, but it causes the other thing to be oxidized. Because remember, you can't have one without the other. Okay? Can't have one without the other. So back to that same equation of sodium and chlorine. Okay? We said sodium was what happened to sodium? Was it oxidized or reduced?
50-50 shot.
Well, it's right there. It's actually more than a 50-50 shot. It's actually right here. Whoops. Okay? Sodium was oxidized. So that makes sodium the reducing agent. because it caused chlorine to be reduced. Chlorine was reduced, so it is the oxidizing agent because it caused sodium to be oxidized.
Watch me mix up this whole thing on because
What?
nothing.
Okay. All right. So to recap, there's a little picture there to help you understand that if whatever is oxidized is losing electrons and it's the reducing agent. Okay? Because it causes the other thing to be reduced. So that's why it's called the reducing agent. Okay? And then whatever is reduced gains electrons. It causes the other thing to be oxidized, so it's the oxidizing agent. And that is the end for today.